And now we have a theorem about quadrilaterals that can be inscribed in a circle. These quadrilaterals go by many different names, such as cyclic quadrilaterals, but we're going to explore what properties they have. We learned earlier, previous chapters, that certain special quadrilaterals, for example squares, rectangles, and isosceles trapezoids, for instance, can be inscribed in a circle. But I can manipulate this figure so that it doesn't seem to be any of those special quadrilaterals. So what property do they share? And it's easy to see if we just eliminate the segments. Let's just look at the four vertices on the circle. And let's just start by drawing rays. From the vertex F, the red vertex, we'll draw a red angle which intercepts the red arc, and opposite that would be the blue angle which intercepts the blue arc. If I consider here that the two arcs, that would be this red arc plus this blue arc, make a complete circle, that's 360 degrees, and each arc or each angle is an inscribed angle, meaning the angle F is half the red arc, the angle D is half the blue arc. We don't need to know how much the blue or the red arc are. We know that the sum of angle F and the sum of angle D must be exactly half of the sum of the red and the blue arc. So I can extend this logic, and let's just do away with those for a minute. Let's draw them from the other perspective. From vertex E, I'll call this the green arc, intercepted by the green angle. The green angle is half the green arc, and the magenta arc is intercepted by the magenta angle, which is exactly 1/2 of that. So the logic continues, and we can see that these two arcs added together must also be 360, and the two angles, each of them being half of their respective arcs, must add up to 180 degrees. So in the end, all we've got is that this quadrilateral can be described by opposite angles being supplementary. And here's an exercise set from section 10.4, number 19. We're given that we have a parallelogram QRST, and you can see from the markings, opposite sides congruent, opposite sides parallel. Also, we know that the diagonals bisect each other. So the blue diagonal and the red diagonal bisect each other. We'll say they meet at the point C. Let's put in a few circles here. And this represents a circle centered at C passing through where the blue diagonal's diameter. Here is a circle with the red diagonal, a diameter. I would have to manipulate this figure to make the two circles one, and you can see, of course, it's going to become a rectangle. So the angle at R must be a right angle. And now we're going to explore some of our special quadrilaterals. We're going to start with a square, exercise 20. A square, yes, it can always be inscribed in a circle when I look at this figure, because each of the diagonals, they are perpendicular, they bisect each other, and they're congruent, properties that we knew from chapter 8. So yes, I'm going to say a square can always be inscribed in a circle. Rectangle looks very similar. Next exercise, 21. Similar, diagonals are congruent, diagonals do bisect each other. However, they don't have to be perpendicular, as you can see here. This figure is also cyclic. Parallelogram, this is going to be my first no. As you can see here, there's no requirement. The diagonals do bisect each other, but they don't have to be congruent. In this special case, then it becomes a rectangle. So unless it's a rectangle, it's not. Therefore, I'm going to say no. How about a kite? A kite could be inscribed in a circle, but only in this special case. And in this case, then each of these would have to be 90-degree angles, because this must be a diameter. And therefore, I'm going to say no to the kite. Rhombus looks an awful lot like the parallelogram. Same situation, unless it's a special case where it happens to be a square. Otherwise, no for the rhombus. Isosceles trapezoid, most interesting of them. On the surface, you might not see this one, but an isosceles trapezoid is inscribed in a circle. And let's prove it really quick. 1 and 2 are supplementary because parallel lines imply consecutive interior angles are supplementary. Angle 2 and 3, well, the base angles of an isosceles trapezoid are congruent. And finally, I can just replace with angle 1 and 3 are supplementary. I'll prove that using substitution. Opposite angles, 1 and 3, are supplementary. Just run through the same exercise for angles 2 and 4, and there you have it. Both pairs of opposite angles are supplementary. This figure is cyclic. Well, this exercise, number 15 in our homework, is really an algebra exercise. We need to solve for the variables, so we need an expression for angle M. We can see it intercepts the arc JKL, which would include the orange and the red arc. And notice the orange arc is missing, so we could do this one of two ways. Let's do the direct method. I'm just going to add these all up, green, blue, red, take it away from 360. The orange arc is 66. And if I do it that way, then I can figure out, well, this angle, angle M, intercepts a 176-degree arc. And once I know that, I can just set 4b equal to 176 divided by 2. Because remember, the inscribed angle is half the intercepted arc. And the arithmetic, I'll get 22 for the variable b. And now that I know 66 is the orange arc, I can see that angle L intercepts the green and the orange. So L is going to intercept 120 degrees. And I can set up this way. So 3a is equal to half of 120, or 60. So 3a is 60, a is 20, and we're finished.